All right. So last time we learned about Faraday's law of induction. And to recap quickly, Faraday's law of induction says that if you've got a magnetic field that changes over time, that it creates a what we call an EMF or a voltage, which is basically the result of an electric field. And the reason that's something new is that because in chapter 18, when we learned about electric fields, we attributed electric fields to the existence of charges. If you've got charges, they create electric fields all around themselves. But this Faraday's law of induction says that actually there's another way that you can create an electric field. That is by having a magnetic field that changes with time. And that will also create a new way of creating an electric field. And so we're going to play around with that a little bit more today. What I want to consider now is, let's imagine that I've got a place where you have a uniform electric field. The electric field is the same magnitude and same direction over some region of space. And what I'm going to do is I'm going to have an object move around inside that region of space. So, oh, my camera got moved over the weekend. Okay, there we go. So imagine I've got some region of space, and in that region of space, the magnetic field points straight up out of the page. So I'm going to draw remember the little dot is like the tip of the arrow coming at your face. And I'm trying to draw these as best I can, sort of evenly spaced. There's another row down here. So evenly spaced magnetic field lines, the lines are coming up out at your face. And imagine that I've got some little rectangle of wire. And I'm moving that rectangle of wire from this location to, maybe I move the entire thing over to this new location. So as I move from point A to point B, what will my induced EMF be? Well, in this case, you won't expect to have one, because according to Faraday's law, the induced EMF is given by the rate of change of the flux. But because the magnetic field is the same everywhere over this entire region, and because the flux is BA times the cosine of the angle between B and A, what's going to happen is when I'm over here in this region, the strength of the magnetic field is some number, right? But when I move to this region, because the magnetic field is uniform, the magnetic strength is the exact same number. That never changed. The area of my little loop, well, the area in the loop didn't get any bigger or smaller, so the area of the loop is the same. The angle between B and A, well, here I have the magnetic field pointing out of the page. The area vector is perpendicular to the region, which is also out of the page. So in this example, the angle is 0, the cosine of 0 is 1. And so what's going to happen is going from here to here, it doesn't matter what B is or how big this rectangle is, moving inside a magnetic field that's uniform is not going to create any kind of EMF. I can move around uniform magnetic fields all day long and get no net EMF. However, if I have a situation where the magnetic field is not uniform, where the magnetic field changes from place to place, then we have a different story. So how does that story change if I make the magnetic field non-uniform? Well, let's have the same sort of region we had the first time, except this time I'm going to have a firm boundary. There's going to be an edge beyond which the magnetic field is going to drop off to 0. And what's going to happen is I'm going to start with my little rectangle fully immersed in the magnetic field. But out here, there's no magnetic field. And so I'm going to move my little rectangle so that it extends beyond the border of the magnetic field. The magnetic field is going to be constrained to this region right here. And so what's going to happen is, as I move this thing out of the magnetic field, there's going to be some section of this loop which no longer is inside the field and therefore doesn't have any flux through it. I still have flux through this region, but before I had flux through the entire region. And so in this case, I'm clearly going to have some sort of induced EMF. So what's that EMF going to look like? Let's figure it out. So we know that Faraday's law says this. And remember, the flux is BA times the cosine of theta. Now, the easy part to evaluate is the theta part, because the theta part is going to be 0, just like it was previously, right? The area vector points out of the page. The magnetic field, in this case, points out of the page. So this is going to conveniently turn into 1. Don't have to worry about that. Now, in terms of how do I do the change in flux, well, one way I can think about it is that the magnetic field in this region is uniform. So B only ever has one value. Let's say that B is, for instance, 5 Tesla. Right? So what's going to happen is the magnetic field over here in this region is still 5 Tesla. B didn't change. What did sort of change is the area of the loop that's inside the field, right? Before, the entire area inside this loop is going to end up being, we'll call it this right here, the length, and this right here, the width. So the area over here would just be L times W. But now what's going to happen is the area that I would have over here is going to end up being L times not the entire W, but just this little section right here. And what's going to happen is I'm going to kind of think conceptually for a second. Because effectively what's going to happen is the area inside the magnetic field got smaller, right? How much did it get smaller by? Because that's what I really care about, is not the amount of flux, but the change in flux. And one way to think about it is that the area got smaller by an amount equal to the area, not of this section, but of the part that came out. So delta phi is going to be B times just the area of the part that left. So I'm actually going to calculate that area rather than this area. So what's the area of this? Well, it's going to be L, and it's going to be times however far I pulled this thing out. I'm just going to call this distance here delta x. It's however far this thing moved outside of my region. So what that tells me is that I can write an expression for the change in flux, and it's going to equal whatever the magnetic field is times the area, which will be delta x times L. Now, going back to that my induced EMF is going to be minus B delta X times L divided by delta T. So here's where I have to stop and think for a second. Think about what all these symbols, right, this alphabet soup that we have written down here, what it actually means. Well, I noticed that I've got the expression delta X over delta T. And that hopefully should ring some bells to anybody who's taken Physics 1, because this is a change in position over a change in time. That's the definition of velocity. So I can replace this right here with the velocity that this thing got pulled out with. It's coming out at a certain speed, and it turns out the faster I pull it out, the bigger delta X is going to be. And so I can write that my motional EMF is going to end up being magnetic field B times L, the horizontal length of my loop, times the velocity that I pulled this thing out with. I'll get a voltage in that size. We call this a motional EMF. Now, what direction is that EMF going to be in? Well, that's all about this minus sign. And usually what happens is when I'm calculating problems for this kind of thing, I usually end up ignoring that minus sign and then figuring it out from common sense after I'm done. In other words, just do BLV, get a number. That's the magnitude of the EMF. And then ask yourself, what's the direction? Because oftentimes the plus or minus is not immediately clear to me anyway. Like, what does minus mean? What does plus mean? I have to translate that into a direction. And the only way to do that is with some degree of common sense. So to make this figure out for me, if I'm looking at the loop right here, I've got a magnetic field pointing out of the page. So I have flux out of the page. Now, when I move this thing outside, the amount of flux I get is getting smaller, right? And so what's going to happen is the induced EMF is going to be trying to keep the flux from going down. To do that, it's going to try to bolster the magnetic field. If the flux is getting smaller, it's going to try to make up for having a smaller A by increasing the B and generating a magnetic field of its own. So it's got to make a magnetic field that augments the magnetic field that's already there. So it wants to make a magnetic field pointing out of the page. Now, if I've got this little loop and I want to make a magnetic field that comes out of the page, the way I can do that is take your right hand, curl your right hand in the direction of the current that's going to flow, and your thumb will point in the direction of the magnetic field. And so you can see that in this case, my current would have to flow counterclockwise in order for my thumb to point in the same direction as the magnetic field. So in this example here, the induced EMF is going to be counterclockwise. Now notice if I did this backwards, if I were to take my loop from the outside and shove it into the magnetic field, well, in that case, what's going to happen is I'd have the same magnitude of the change, right? Except now what would happen is I'd go from having zero flux on the outside to having non-zero flux on the inside. So the flux would be increasing, and the induced EMF doesn't want change to happen, period. So if the flux tries to get bigger, what it's going to try to do is to keep the flux from getting bigger by trying to reduce the size of the magnetic field as the area would increase. So if that were the case, if I were to do this same experiment backwards and push that in, it would want to make a magnetic field in the opposite direction of B. So in that case, it would have been clockwise. So, you know, anytime you have a problem like this, think about what kind of flux you've got, think about what kind of flux you're changing to, and realize that the induced EMF is going to be in whatever direction opposes that change. If the flux is getting bigger, it's going to try to reduce the magnetic field. If the flux is getting smaller, it's going to try to increase the size of that magnetic field. And if you think about it in those terms, you can't go wrong. Now, one cool thing notice in this first example, as I'm pulling this thing outside, I'm getting a counterclockwise EMF. Now, because I have a counterclockwise EMF, that means I'm going to have counterclockwise flowing currents. And if I have current flowing around this loop, that means there's going to be a force generated by the magnetic field, right? There's currents that will respond to magnetic fields, and we have a version of the Lorentz force law to talk about those. So what was that Lorentz force law expression? It was I cross times L cross B. And this is kind of interesting because if I've got current that's flowing in the same direction as my EMF, which is usually the case, I can find the direction of that force by just thinking about the right-hand rule for a second. So let's do that real quick. What's going to happen is the current is in a different direction on each of the four sides of this little rectangle. Now, on this side of the rectangle, there's no magnetic field. So there's no force acting on this side of the rectangle. Now, what about on the top of the rectangle? I've got current that's traveling to the left up there on the top. And if I do the right-hand rule, my current is to the left. I'm putting my fingers in the direction of the current. But then I have to bend my fingers in the direction of the magnetic field, which points out of the page. That means I have to rotate my hand, palm up, so I can bend my fingers appropriately. And when I do, my thumb is going to point in the direction of the force. So what that tells me is that this top part of the wire is going to get pushed upward by the magnetic field. However, what's going to happen is down here at the bottom, I have the opposite effect because the current is going around counterclockwise. So on the bottom, the current is to the right. And there, if I do the right-hand rule, I take my fingers in the direction of the current, I bend my fingers towards the magnetic field, and my thumb points towards the bottom. And from symmetry, these two forces are going to be equally strong, so they're going to cancel each other out. So there's not going to be an up or down force as I yank this thing out of the magnetic field. However, on this section of the wire, the magnetic field is going to point towards the bottom of the page. So if my current points that direction and I bend my fingers out of the page, my thumb points to the left. And so what's going to happen is there is a force to the left. And what's that going to look like to me? Well, as I try to drag this thing out of the magnetic field, it's pulling to the left to try to slow me down. I'm going to feel something yanking it back to the magnetic field. And the bigger the induced EMF, the bigger the current, the bigger the force. So the harder I yank it out, the harder it pulls back on me. Now, it can't ever pull hard enough to stop it, because if it ever pulled hard enough to stop this thing from moving, then the flux would stop changing. If the flux stops changing, the EMF goes away. If the EMF goes away, there's no more current, and no more current means no more force. So it will always slow the thing down, but never quite stop it. But what's going to happen is, as I pull this thing out to keep that speed constant, I'm going to have to do work. And it's the work that I'm doing that's providing the energy for those currents to flow. All right, so that's the idea of motional EMF. It comes up from time to time. I know that when I started graduate school, literally the first project that I had in graduate school for what would eventually become my dissertation work was we were doing an experiment that involved having a sample that would vibrate back and forth inside a magnetic field. And the idea was that the magnetic field would be in the middle of the sample, and we were just kind of dragging that magnetic field region back and forth across my sample, because that was going to create some things called vortices that moved around. We were tracking the motion of those vortices. And in theory, it's super easy to say, I want to create a magnetic field that is uniform, right? In theory, I can always imagine that super easily. Yay, we just did it. But in the real world, it's very difficult to make a magnetic field that's completely uniform. And so in our experiment, we knew that the magnetic field that we wanted to be uniform would probably vary by about 1% from one side to the other. And the whole sample was about 2 inches across. And so my first job as a graduate student was to figure out how big the induced EMF was going to be from moving this sample back and forth. Because that induced EMF that we were hoping would be 0 was in reality going to be something non-zero. And if it was too big, we wouldn't be able to see the signal that we were trying to see, and our experiment wouldn't work. So in theory, our experiment would work great, but in practice, it might not because of limitations in our ability to create the thing in our imagination. So that was a really big thing that I had to bump my head up against and struggled for years to try to minimize this motional EMF in an experiment where I had to have a thing moving around inside a magnetic field. It also, is going to be the source of a lot of kind of the jitter that you'll often see in electrical devices. You'll see voltages that are maybe not completely constant, and a lot of that comes from EMF of just things moving around. You can use this sort of thing for airplane speedometers, BLV. Oh, look, V might be the velocity of my plane, right? So sometimes this is a useful thing, but it's at least something you have to be aware of. All right, so that was easy enough. Let's take another kind of example of this motional EMF, and this may not work well. Let's see what happens. So what I'm going to do is I'm going to share my screen. We are going to go and watch a YouTube video and hope that this garbage YouTube video resolution is easily visible as I stream a copy of a stream. All right, so this is like a little tiny, like 18-second video. Come on, dude. And go. So what's going to happen? Let's full screen this bad boy. So hopefully this is intelligible. So what you have here is a big aluminum block. This thing, God, it's got to weigh at least 30 pounds. It's huge. And what these people have done is they've gone to an MRI, and they're about to do a little experiment with this aluminum block. And in order for us to understand what we're about to see, you have to know two things. One is that MRIs work by generating enormous magnetic fields. Somewhere in the region between 5 and 10 Tesla is my suspicion. Certainly it's upwards of 1 Tesla. It's a large magnetic field that you don't normally see. The second thing you have to know is that aluminum is not magnetic. It is diamagnetic, and only weakly so at that. So you should not expect the magnetic field alone to affect the piece of aluminum. That's why if you stick the thing into the MRI, it's not going to get like picked up and slammed into the sides and break stuff the same way that like a piece of iron might. However, it also has a large area, which means if you put it inside the magnetic field, you will be generating flux. And so right now what they're going to do is they're going to take this big block of aluminum and they have it outside of the MRI where the magnetic field is basically pretty close to 0, and they're just going to tump it over. And boom, it does exactly what you expect. But now they're going to put it inside the MRI where the magnetic field is big, and look what's happening. This thing is slowly but surely crawling to a stop. Let's replay that. Go. So, thump, everything we would expect inside the magnetic field. It slowly but surely, it still falls, but it falls very, very gradually. Now, go. How does that work? What's going on there? Well, in order for us to make sense of that, our YouTube, I'm done with you. Thank you. In order to make sense of that, let's break it down. Again, messy table. So what's happening inside this thing is you've got this big rectangle that we're going to look at from the side, and you've got a magnetic field that's uniform, and it's creating flux through that surface. If I could, draw 3D to save my life, right? What's happening is those magnetic field lines are going right through the surface, and the area that they're penetrating is the area of that front face, right? So that's the area that's creating flux. Now, what's going to happen is, as this thing tumps over, originally there's magnetic field lines that are going through the very, very top of that region, but as it tumps over, what's going to happen is now some of the magnetic field lines that used to go through it are going to now miss the top. The flux is getting smaller. Now these lines are still going through. So the amount of flux I have is somewhat reduced because I'm missing lines that used to go through the top. So my flux is getting smaller. Now, what's the effect? If I have flux through the face of this thing that is getting smaller, then what's going to happen is it's going to try to generate an EMF to keep the flux larger. And it will do that by trying to bolster the magnetic field. So how's that going to happen? Well, in order to make the magnetic field point this way, I'm going to get currents that flow. If I'm looking at it from the left side, the currents are going to flow counterclockwise. We call these eddy currents. And these eddy currents are going to flow swirling around counterclockwise. Roscoe, enough, buddy. And it's those currents that are causing the magnetic force that keeps that thing from falling down. Now, to think about like what those forces should look like, I'm going to draw kind of a front facing. Imagine you're looking at just the rectangle on the front of that piece of aluminum. The currents flowing counterclockwise. So let's go. So your current's going to look like this. And the magnetic field, if I'm looking at this from the left side, the magnetic field's coming out the front. So B is basically pointing toward my face from this perspective. And what that means is that when I do the Lorentz force law, IL cross B, let's retire this red one forever. What's going to happen is over here, L cross B is to the right. Over here, L cross B is to the left. So the left and right sides of this aluminum block are getting pulled sideways, but those two forces cancel out. However, what's going to happen is the bottom of this guy is going to get pulled downward. The top of this guy gets pulled upward. Notice the net force on the block is going to be zero because all the up forces and all the down forces, they cancel. However, it's easier to see when I look at it from the side that what's going to happen is the downward forces are all acting at the bottom of the block. They're pulling it down like this. But the upward forces are all acting at the top of the block. They're pulling like this. So even though they don't generate a net force, they will generate a torque because it's pivoting around an axis right there. So the torque created by this will be zero because the moment arm is zero. But this guy here has a moment arm that's quite large. And that's going to generate torque. And that's why it rotates more slowly than you'd expect. Because you have two torques. This torque making it want to rotate clockwise, and the torque from gravity making it want to rotate counterclockwise. So Max, enough. I hate dogs. Why do I have dogs? So these eddy currents, they form even in solid objects. And those eddy currents can sometimes cause surprising results. If you've ever seen a movie where they use an EMP or an electromagnetic pulse, movies always get those wrong. It's said that they often would happen if, like, you had a nuclear explosion or just a very large magnetic field that ramps up super huge for a short period of time and then turns off suddenly. And in movies and TV, EMPs are always being used to disable electronic devices. Suddenly your computers will stop working. If it's a sci-fi film, the robots will all shut down. And the idea of an EMP is a real thing, but in real life, the reason that the EMP would cause all of your computers to stop working is because you would have conducting surfaces, much like this, and you would have a brief moment where the magnetic field ramps up super huge and then turns off again. So you'd have huge induced EMFs. Those huge induced EMFs would create very large eddy currents, such large eddy currents that the heating that you get from those large currents would cause things to burn up. And so, more than likely a real life EMP would probably cause, like, your iPhone to melt in certain locations. They might spark or catch on fire. And of course, even non-electronics would also be similarly affected. You get pulses of eddy currents in, say, the body of your car, which could cause any number of responses, little sparks and such like that, as the voltages jump up to something super huge for a brief instant. But that's what you're dealing with there, is these things called eddy currents. All right. So let's see if we can't take this idea of electromagnetic induction and let's see what it has impact on when we deal with circuits. Let's combine what we've learned here in chapter 23 with what we've learned in chapters 20 and 21. And in order to do that, we're going to have to focus in on a particular effect that you often see when you have a current in a circuit that changes with time. And this was first noticed by a guy by the name of Joseph Henry in the 1800s. And I love this guy. This is one of my favorite physics stories. Because what's going to happen is this guy, Joseph Henry, was working with coils, solenoids, which we talked about previously in chapter 22. And as the story goes, Mr. Henry was working with these solenoids, and he noticed that every time he'd send current through the solenoid and make a big magnetic field and do his experiments, that when it came time to unplug the solenoid, what would happen is he'd unplug it, and very frequently he would get shocked. It's like, geez, that hurts. But he noticed that in his experiments, he had lots of coils of different shapes and different sizes. And even though he got shocked a lot, he noticed that he got shocked worse with some of the coils than with others. And he's like, that's weird. So allegedly what this guy does is he gets a bunch of coils with different sizes and shapes. He sends lots of current through them and then unplugs them and pays attention to the shock that he feels when he unplugs these things. And he calibrates his measurements based on how far up his arm does he go numb, right? Does it go numb to my first fingertip? Does it go numb to the end of my finger? Does it go numb to my elbow, right? The size of the shock is going to be related to how bad it hurts when he unplugs these. And so he does apparently a lot of these experiments where he's just all these different solenoids. He's sending current through, unplugging them suddenly, and measuring the shocks. And he ends up determining the impact of the size and the shape of the coil on the size of the shock. And as a consequence of this, we're going to name a unit after this guy. But to sort of think this through, let's see if we can't break down what Henry was experiencing. So he's got a coil. And what's going to happen is he's sending current into that coil. And back in chapter 22, we learned that when you send current through a coil, you generate a magnetic field. This is called a solenoid. And the magnetic field generated by that solenoid was given by mu naught, the constant, times little n, that's the number of turns per unit length, divided by however much current that you send through it. So again, little n is going to be capital N divided by L, where capital N is the total number of loops and L is the total length of the solenoid. And so what's going to happen is if you got a solenoid with a whole bunch of loops, little n is going to be really, really big, and I'm going to get a lot of magnetic field. If I have a small number of loops, or if the solenoid is quite long, and so the loops are very, very widely spaced, that's going to give me a wimpy magnetic field. So the size of my magnetic field is going to depend on those factors. Now, what is Henry doing? He's sending the current in, but then he's unplugging it suddenly. And what that means is that when it's plugged in, I'm going to have a magnetic field that's large. When I unplug it suddenly, it's like I'm dropping the current to zero instantaneously. Now, when I drop the current to zero instantaneously, I'm dropping the magnetic field to zero nearly instantaneously. And remember, Faraday's law says if the magnetic field changes with time, I get an induced EMF. So conceptually, this is what's happening to Faraday, or to not Faraday, to Henry, is he's trying to turn the solenoid off by disconnecting it from the battery so the current goes away. But the solenoid is like, no, 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 I've got all this flux through all these loops. I don't want that flux to go away. And so when I try to turn off the flux, it tries to generate an EMF, a voltage of its own, to keep the current going. And the reason that Henry is getting shocked is because as he suddenly unplugs that coil, the voltage across the coil is jumping up and becoming super, super large to try to make the current keep coming. And you may have seen this effect yourself. If you've ever taken something that's like drawing power from an electrical outlet and you unplug it without turning it off first, what's happening is you've got probably coils inside that device that the magnetic field is trying to drop off to zero instantaneously. And so they are causing a huge jump in voltage. And sometimes that's just enough to cause a little spark at the outlet. And so when you unplug it, you might see a brief spark as it tries to keep the current going, even though you've disconnected it. Now, it can't last forever, and eventually it will peter out. And the same thing is happening here with Henry. He gets a brief shock, but he's not electrocuted lethally because the current can't maintain itself over time. So that's what's happening to Henry. He's getting that. And the size of the voltage that he gets is going to be given by Faraday's law. But remember, the change in flux is going to be the change in BA cosine theta, right? That's what flux is, right? But wait a second. If I'm trying to find the change in flux, well, the area of my loop, that's not changing, right? That's given by the shape of the coil, and that's staying the same. I'm just going to pull this out of that little delta. So I have A, and the cosine of theta, that's not changing. In fact, that's probably just 1 because the magnetic field points along the axis and the area vector points along the axis. So that's not changing. So it's really just A, the area, times delta B. Now, this is the area of one loop, and I've got a whole bunch of loops. So I'll have to probably multiply by the number of loops. Okay, whatever. So really what's happening is I'm getting the change in flux because B is changing. The thing that's changing is B. Oh, but wait a second. B is given by this. And even within that, B is changing, sure, but mu naught is a constant. That's not changing. Little n, that's the number of loops, not changing. The length of the solenoid, not changing. So mu and n are not changing. So really, when I think about delta B, what I really care about is the change in current. That's the thing that's changing. The current's going from being very, very large to being 0. So I could write the change in flux as being n times A times mu times little n times the change in current. Okay. But wait a second. Little n is capital N over L. So I'm going to have capital N times capital N, n squared A times mu times delta I over the length of my thing. Oh, but wait a second. I'm finding the EMF. So it's going to be all this divided by delta T. So I've got, what is it? Let's put mu naught out front. It's a constant. I've got n squared. I've got the area of the loop. I've got it over L. And I'm going to write delta I over delta T off to the side because it makes it easier to parse what's going on. So again, all I did is I just pop this up into there. So wait a second. All this garbage out here, those are constants. And this right here is the rate at which I change the current. And of course, there is a minus sign because it opposes the change. So I'll slap that minus sign out there. So what Henry was experiencing was that the size of the voltage, the size of the shock that he felt, well, it depended on how fast he unplugged it, which is rapidly, right? If you're pulling that off, this becomes super, super huge because you're going from big to 0 in short amounts of time. But it also depended on all this stuff. And this is all stuff that has to do with the size and the shape of the coil. And lo and behold, according to this, he's going to feel a larger shock if the coil has a large number of loops. And in fact, it goes as n squared. So if you go as n squared, that means that if you double n, you're going to quadruple the size of your voltage. So the EMF he felt, the shock that he got when he unplugged things, was highly dependent on how many loops. More loops means way bigger shock. It also depended on the area. If I had a big fat solenoid, I was going to get a bigger shock than if I had a little skinny solenoid. It also depended on the length. The long solenoids tended to get less of a shock than the little short squat ones. Right. So all of these factors had to do with the size and the shape of the solenoid, and they determined how much of an induced EMF you got when you tried to increase or decrease the current. So what Faraday realized was that these geometric factors, he could break those out, and we're going to give that a name. We're going to call all this garbage here the inductance. L. And for a solenoid, the inductance is going to be all this garbage right here. Now, this expression is only true for a solenoid. If you had wires of some other geometry, you'd get some other more complicated expression that we're not going to learn. Just like back in chapter 19, when we had capacitors, We always did the capacitance for a parallel plate capacitor, a particular kind of capacitor. But if you had different shapes, you might get something else that's way more complicated, but beyond the scope of this class. And in practice, what ends up happening is any circuit is going to have some sort of inductance to it. And usually you can't calculate it from some formula. You just have to go out there and measure it. However, if you replace all this with L, you find that the induced EMF is going to equal the inductance times the rate of change of the current. And that's going to be the definition of inductance. So we say that and so this L may or may not be that formula we just did. It may be something more complicated, but still this expression is always true. So again, what does inductance tell me? It mostly just tells me how much that particular wire or circuit element or whatever, how much it tries to resist having you change the current. Because of inductance, if you try to change the current inside something, then sometimes there'll be an EMF that will fight back against you. So if you try to make the current bigger, it's going to push back. Try to make the current smaller, it's going to pull forward. And it basically gives you kind of a measure of how hard a circuit will resist allowing you to change the current. It comes about because of Faraday's law and Faraday's law acting inside your circuit. Very frequently, we will say that elements of the circuit that have inductance are called inductors, just like things that have capacitance are capacitors. So an inductor in a circuit, we will draw as a little coil, and it'll have some inductance L. The unit of inductance, named after Mr. Joseph Henry. So we're going to measure inductance in Henrys. And we'll be able to deal with circuits that include inductors. Let's start with a DC circuit that uses an inductor. We'll start there, and then we'll be able to switch our thinking into alternating current circuits, which we talked about briefly in chapter 20, but we're going to do them in earnest in this chapter. And we had to wait for this because in an alternating current circuit, what's going to happen is your current is constantly going forwards, backwards, forwards, backwards, forwards, backwards, which means in an AC circuit, delta I over delta T is for sure very non-zero. It's going to be all over the map. And if you have any element of your circuit that has inductance, then what's going to happen is when you try to make delta I over delta T one direction, it's going to push back at you in the other direction. It's going to create a voltage. So we couldn't understand the physics of any alternating current circuit until we understood how to deal with this voltage. But let's do DC first. Let's imagine that I've got the following circuit. I've got a DC battery. I've got a resistor. And then I'm going to hook it up to an inductor. And I want to think about what I can figure out in this DC circuit. So let's call this V total. That's the voltage of my battery. That's obviously R, and this has an inductance L. And a circuit like this we would often refer to as an RL circuit because we're not very creative. It's got an R, it's got an L. It's an RL circuit. So let's think through what we know. Well, one of the things that we know about circuits are Kirchhoff's rules. Right? And we know that Kirchhoff's junction rule says that the current only ever changes at junctions. And there are no junctions in this circuit, right? This is one continuous flow. And that tells me that the current all the way through this thing is the same. There's only one current in this entire circuit. The loop rule, however, tells me about voltage changes. And it says that if I go around any loop and I add up all the voltage changes, those voltage changes will equal 0. Now, imagine I start here and I go around this loop clockwise. I'm going to cross that battery. That's going to give me a voltage increase of V total. But then as I continue, I'm going to go across a resistor, and I'm going across a resistor in the direction of the current, which means I'm going to get a voltage drop, so minus, and the voltage across a resistor is equal to I times R. That's from Ohm's law, V equals IR. But then I'm going to go across this inductor. And the thing about the inductor is that the voltage across an inductor, I'm going to get from this. The voltage drop across the inductor is going to be L, the inductance, times the rate of change of the current. So what's going to happen is when I hook this circuit up, it's going to have to at all times obey this equation. Now, this is a non-calculus based class, but for those of you who have taken a little calculus, I'll point out that delta I over delta t, that's the rate of change of the current. That's really a derivative. And so what we've got is this really, really complicated equation that says that the current that I get is going to be related to how fast my current is changing. It's the rate of change in the same equation as the thing itself. Boom. Now, this is called a differential equation, which if you take you have an entire class on how to solve differential equations. It's not required for this course, so I'm just going to tell you the solution for this differential equation, and you're not going to have to learn how to solve them legit. But conceptually, hopefully it should be easy to wrap your head around why the solution looks like it does. And one way to think about it is if I first build this circuit, right? If I'm making the very last connection, I'm just about to plug this thing in, the split second before I plug it in, I don't have any current flowing in the circuit at all. So at the very first instant that this thing is connected, the amount of current I have at that moment is 0. Now, if that's the case, this is 0, this middle term goes away. And in order for this equation to be true, V total is going to have to equal L delta I over delta T. In other words, this has got to be just as big and negative as this is positive for this to equal 0. So when this term goes away, this term is going to have to be really, really, really big. I'm sorry?
Did you mean, so V total equals negative L and delta I over delta T, or just delta I over delta T?
Well, so if I imagine that this thing equals 0, I have V total minus L delta I over delta T equals 0, right? But if I move this to the other side, at that moment, this voltage and that voltage have to be the same.
Okay.
That's all I was saying. So if this was 10, this would have to be negative 10, right? So 10 minus 10 would be 0.
I got it. I just wasn't sure if it was including the L or if it was excluding the L.
You know, it's definitely including the L. L times delta I over delta T, this whole thing would have to equal whatever V total is.
Right.
But here's the thing. L is a number that's not going to change. It's like a constant, right? So what it does mean is that when this, if this is true, delta I over delta T is going to have to be some non-zero constant. It's going to have to not be 0. So when this is equal to 0, delta I over delta T has to not be 0. And in fact, how do I interpret that? Well, imagine I was doing a graph of what the current has to look like as a function of time. Now, at time 0, we said that we were starting off with no current at all. So the current may be 0, right? But delta I over delta T, well, that's delta I is the rise of my graph. Delta T is the run of my graph. And so what it says is that at least initially, delta I over delta T is going to have to be big to make this be big enough to cancel that out. So I'm going to have to start off at 0, but it's going to have a positive slope. However, the second that the current stops being 0, as this gets bigger, this is going to have to get smaller for the equation to stay true, right? And that means the slope may start out really steep, but it's immediately going to have to get less steep and less steep and less steep. So my line is going to not be a line at all. It's going to be curved, and it's going to be curved concave down. So I've got a line that starts off at 0, and it's going to bend downward. And the bigger the current gets, the higher we go, the flatter it's going to get. However, as I gets bigger and bigger and bigger, and delta I over delta t gets smaller and smaller and smaller, at some point, this is going to get so small, it's going to become 0, right? Now, a 0 slope is a horizontal line. And when that happens, well, if delta I over delta t becomes 0, that means the current's going to stop getting bigger, which means I is going to be the biggest it ever gets when this equals 0. But now I just have V minus IR equals 0, or V equals I times R. So if I do that, V total minus IR equals 0. That means that V total equals I times R. That looks just like Ohm's law. V total over R equals I. So when this becomes 0, the current's going to equal V total over R. And that's the biggest it's ever going to get because it's no longer changing anymore. So this is the biggest current I will ever see. So what's that going to look like on my graph? It's going to go curve down until it's going to get flat. And eventually it's going to go flat. And if you were to kind of see where it levels off at, it's going to level off at I max. Does this look familiar at all? Hopefully it looks a little familiar. Because back when we did capacitors, we did RC circuits. And for an RC circuit, the charge on the capacitor looked exactly like this. It started off at 0. It at first was super steep, but then it bent downward and leveled off to some Q max. And in fact, we know what kind of equation is going to give me that kind of behavior. And so even without doing the calculus, I can write down the answer. The current at any given moment is going to have to equal whatever I max is times 1 minus e to the negative t over some constant tau, where tau is called the time constant of the circuit. Now, back when we did RC circuits, the time constant was R times C. But for an RL circuit, the time constant is going to be something a little bit different. The time constant for an RL circuit is going to be the inductance divided by the resistance. To see that that works, think about the units for a second. So if I have resistance on the bottom, I know that resistance is volts per amp, right? What about inductance? What the heck is a Henry? Well, if I want to figure out what a Henry is, let's just take this and rearrange it. So this over here is volts. So I have volts times whatever a Henry is. And then this is amps per second. So if I rearrange that, a volt second per amp is what a Henry is. So now, if I have volts seconds per amp divided by volts per amp, remember when you divide by a fraction, it's the same as multiplying by reciprocal. So that's volts seconds per amp times amps per volt. The amps cancel, the volts cancel, and lo and behold, I get straight up seconds. So taking an L and dividing by an R is going to give me a unit of time.
I got it.
Yeah. So pretty neat. Notice that just like with RC circuits, what's going to happen is this characteristic time is going to tell me how much current I've got. If you allow t to equal 1, whatever the time constant is, I'm going to have e to the negative 1 power, and that's like 32%. So 1 minus that's going to be 60-something percent. Actually, it's more like 36.5%. This ends up being like, I want to say it's like 63.2%. So after one time constant, or sorry, if t equals 1 tau, the current is going to equal about 0.632 times I max. So if you wait one time constant, you're going to be about 63.2% of your way up to your maximum current. But if you wait 2 time constants, then what's going to happen is it'll have jumped up to about 84%. If you wait 3 time constants, it's going to jump you up to about 95%. After 4, it's like 98. After 5, it's like 99 point something. And in order to get all the way to 100%, you'd have to go to infinity seconds. This would have to become infinity over here, which is never going to happen. But after about 4 or 5 time constants, you're basically there. And so typically what we will end up doing is saying that after a long time, which in our case is more than about 4 or 5 times whatever the time constant is, the current will equal I max. And we can solve problems with this the same way we did RC circuits a number of chapters ago. The only difference is that when we did RC circuits, it was the charge on the capacitor we were plotting, and here it's the current in the inductor that we're plotting. Also note, this is what happens if I'm ramping up the current in my inductor. But I could just as easily imagine a situation where the current in the inductor is large and it's becoming small. Consider. Imagine that I've got a battery and a resistor and a 3-way switch. Here's an inductor. Here's a second resistor. And my switch can either go to position A or position B. So it's either like this in one position or like this in the other position. Now, if this is, let's say, 1,000 ohms, let's say that this is 10 henries, and let's say this is 500 ohms. And I start off with the switch in position A. For a long time. Right. Then I'm going to change this, move the switch to position B. And what I'd like to know is what's the current going to be like, let's say 2 seconds later. Now, what's going to happen is if I start off with this circuit in position A, then what I've got is a complete circuit around the outside. So current's going to be flowing around the outside. And as the current increases, it's going to obey this equation here while charging up. And of course, if I'm waiting for a long time, the way I should read that is infinity seconds. Let's have this be 15 volts. So after infinity seconds, e to the negative infinity is 0, which means this whole thing becomes 1. So I is going to equal I max, and I max is going to be V total, 15, divided by R. Now, what should I use for R? Okay, thought you would answer. So the R in question, well, I have a 1,000 ohm resistor here and a 500 ohm resistor here. And since they're both in series with each other, because if I go through one, I have to go through the other, I'm going to combine them into one equivalent resistance and say 1,500, because resistors in series just add. And so 15 divided by 1,500 is going to be 0.001 amps. So I'm going to have a current of only 1 milliamp in this circuit. Now, that's what current I start with. But what's going to happen is when I flip the switch to position B, at that moment in time, I've got a whole bunch of current flowing through that inductor. And when I switch to position B, suddenly my battery is disconnected. So you would normally expect that to turn off the current. You would expect the current to drop to 0. But what's going to happen is the inductor doesn't want to let the current drop to 0. Faraday's law is going to try to make it keep the current going. So it's going to generate a voltage on its own. The inductor is going to kind of act like a battery in this circuit to try to keep the current flowing. But if it could keep the current flowing, if it could keep the current from dropping at all, then the induced voltage would just go away. So it's going to keep the current flowing, but it won't be able to win in the long term. But what it can do is it can make it turn off more gradually than we expected. So while discharging, what's going to end up happening is we're going to have a very similar looking function, except the graph will have to start off at I max and decrease asymptotically. And that we can guess from common sense is going to look just like the discharging capacitor did. So we'll be able to use that expression. So how will we get this? Well, the time constant is going to be L divided by R. Now, wait a second. L in this case is 10 henries. R, however, well, if I'm using this circuit right here, this 1,000 ohms is no longer even a factor. So the R in this case is going to only be the 500 ohms. So if I take 10 divided by 500, that's the same as 1 divided by 50. So 0.05 seconds. And so now what's going to happen is my current is going to equal I max, which is still this, times e to the negative 2 divided by 0.05. And of course, I didn't bring my calculator in here because that'd be too easy. I can't do exponentials, so 2
Isn't 10 divided by 500.02?
I'm sorry?
Isn't 10 divided by 500.02?
Why 0.02?
Yeah, 0.02, not 0.05.
Probably. Wouldn't surprise me if I am stupid. Yeah. My bad. Now I'm going to take 2 divided by 0.05. Or sorry, 2 divided by 0.02. And so this entire thing is 100. So this turns into e to the negative 100 power. And if I take e to the negative 100 power, that's not how it. Oh, you're the worst scientific calculator ever. There we go. So what's going to happen is e to the negative 100 power is so tiny that when I multiply it times 0.001, we end up with like 3.7 times 10 to the negative 44th power amperes, which is so close to 0 that it might as well be 0. Right. So at that point, this is so flat, it's practically at 0. Does that make sense? You see how we handle that kind of thing?
Yes.
So that's RC circuits, or excuse me, RL circuits, which behave just like RC circuits. And that's stuff that you've dealt with before. And notice you can do problems like, how long would I have to wait for the current to be, blah, blah, blah percent charged? You do the same kind of thing. You plug in for I, whatever percent of I max you had, the value of I max will end up canceling. And we've done that kind of problem before. Where things are going to get interesting with inductors is when we stop putting them in a DC circuit and we start putting them in an alternating current circuit. Because an AC circuit is going to make things really, really complicated. And in fact, what we're going to need to end up doing is, for an AC circuit, we're going to have to devise some tools just to be able to parse what's going on. To give you a sense of how that's going to play out, let me build the same circuit, but this time, let's put an AC source in it. So here is an AC voltage. And let's just leave the same resistor and the same inductor. And let's think about what's going to happen just based on the loop rule from this. Now, before we did the loop rule, we had V total, but the problem is that our V total is an alternating current voltage source. So our V total is going to be some V max times like a sine of omega t. In other words, this is going to be something that changes sinusoidally back and forth. So the current's going big and forward, then big and backwards, then big and forwards. It's switching back and forth, back and forth, back and forth. That's annoying. Now, when there's current flowing this direction, I'm going to have a voltage drop across the resistor in that direction. And we know that the voltage across a resistor is equal to I times R. But the problem is, because the voltage from my battery is switching backwards and forwards like this, I expect that my current is going to end up being similarly, some kind of function where it's going to equal some I max times a sine or a cosine of omega t. That seems kind of complicated. Plus, because I have current that keeps switching from forwards to backwards, that tells me that over here, delta I over delta t, that's not going to be zero either. So the voltage across this is also going to end up being some kind of sinusoidal function. But here's where things get really messy. Because what's going to happen is, when the current is at its largest, when the current is super, super big, the voltage across that resistor is going to be super, super big. But when the current is at its maximum, it's getting ready to come back down again. So that means that when the current is at its maximum, it's at the peak of one of these things here. But the slope of this at that moment is zero. And so what's going to mess us up, what's going to make this problem hard, is that when this voltage across the resistor is at its maximum, it's not going to happen at the same moment that this is at its maximum. This is going to get big at a different moment from when this does. And so the timing of these functions are all going to be kind of skewed. If one of them is like this, the other one might be shifted. So that they hit their peaks at different moments. And it's going to make it really, really hard for us to keep track of all these sines and cosines if they're all hitting their peaks at different moments. And so trying to write everything out with all kinds of sines of omega t's, that's going to be a mathematical nightmare. And in order for us to solve this problem, we're going to have to invent a new way of thinking about it that makes the complicated stuff easier to wrap our heads around. So that's going to be our next goal, is to invent that. But I think that's probably not going to be a topic that I can finish in the next 15 minutes. So we're going to end it there, and we'll pick it up on Tuesday, where we'll do AC circuits, and we'll learn how am I going to invent a new kind of math that will deal with these constantly changing factors in a way that we can deal with. And it actually won't be hard at all. But it is going to require a different kind of thinking. So I will let you guys go with that, and I will see you tomorrow. Any last minute questions before I hit the button?
No, thank you.
All right. Have a good one.
See you tomorrow.